How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You are standing in the middle of a crowded stadium. Maybe it is the final minutes of the Super Bowl, or the encore of a massive concert. The energy is electric. 70,000 people are screaming, cheering, and almost simultaneously, reaching into their pockets, they hold up their phones to record the moment, to live stream it, to share it with the world instantly. 10 years ago, this was a dead zone. The network would choke. Your upload bar would freeze, paralyzed by the sheer volume of digital noise. But today, you tap the screen and the video flies. It navigates through a soup of invisible signals, finds a tower, and reaches a server on the other side of the planet in milliseconds. We look at the bars in the corner of our screen, and we just assume that the internet is in the air, omnipresent and infinite like oxygen. We assume that upgrading from 3G to 4G to 5G is just like turning up the volume on a radio, or widening a pipe to let more water flow through. We think it is just more power. But that is not true. The air is not infinite. In fact, the air is incredibly crowded. The radio spectrum is one of the scarcest natural resources on Earth. And by all conventional laws of physics, we should have run out of room years ago. So how does this actually work? How do we squeeze more information into the same empty space without the signals destroying each other? Today on First Principles, we are going to take apart the invisible infrastructure of the modern world. We are going to look at 5G, not the marketing buzzword, but the physics problem. We are going to find out how we learn to stop broadcasting and start pinpointing, and how we turn the air itself into a fiber optic cable. To understand why 5G is such a radical departure from everything that came before it, we have to start with the experience we have grown numb to. We live in a world of instant gratification. You click a link, a movie starts. You press a button, a car arrives. We treat data like it is a utility, as reliable as tap water. But unlike water, which flows through physical pipes that we can see and touch, data flows through the electromagnetic spectrum. When you use your phone, you are essentially holding a very sophisticated walkie-talkie. It converts your voice or your photo or your email into a digital code, ones and zeros. It then turns those ones and zeros into radio waves. These waves oscillate at a specific frequency, radiating out from your phone until they hit a cell tower. The tower catches the wave, decodes it back into ones and zeros, and sends it into the wired internet. It sounds simple, but the problem is that everyone is doing it at the same time. Imagine being in a crowded room where everyone is trying to hold a different conversation. If two people try to talk at the same pitch and volume at the same time, their voices clash. It becomes noise. Information is lost. This is called interference, and it is the mortal enemy of wireless communication. For the last century, our solution to this problem was regulation and segregation. We took the radio spectrum, the range of all possible frequencies we can use to communicate, and we chopped it up. We gave a slice to FM radio. We gave a slice to TV broadcasters. We gave a slice to the military. And we gave a few very expensive slices to mobile phone companies. But here is the catch. The spectrum is finite. There is only so much beachfront property in the radio world. The best frequencies, the ones that can travel long distances and punch through walls, are fully occupied. By the early 2010s, as the smartphone revolution took over the world, we hit a wall. We had billions of devices trying to scream into a spectrum that was already full. The highways were jammed. The room was too loud. This brings us to the pioneers of this technology. They were facing a crisis that looked mathematically impossible. There is a fundamental law in information theory known as the Shannon-Hartley theorem. It is an equation that defines the maximum amount of data you can transmit over a channel of a certain bandwidth. It is a speed limit imposed by the laws of physics. The engineers and scientists working on the next generation of connectivity, what would become 5G, looked at this equation and realized they had three options to get more speed. Option 1, add more power, but that kills battery life and causes more interference. Option 2, find more efficient ways to code the data. We had already squeezed that lemon almost dry. That left option 3, find more bandwidth. We needed more road. But as I mentioned, the good road, the frequencies under 6 GHz where 4G, TV, and Wi-Fi live, was completely gridlocked. There was no space left to build, so the engineers did something counterintuitive. They looked at the bad neighborhoods of the spectrum. They looked way up the frequency chart at the millimeter waves. To understand why this was such a gamble, we need to open the black box of radio physics. Radio waves are defined by their wavelength. The lower the frequency, the longer the wave. FM radio waves are huge. They can be meters long. They are like big rolling ocean swells. They can easily wrap around buildings, pass through trees, and travel for miles. That is why you can pick up a radio station from the next town over. As you go up in frequency, the waves get shorter. 4G signals are usually between 10 and 30 centimeters long. They are pretty good at getting through obstacles, but not as good as FM radio. Now look at millimeter waves. These are the frequencies the 5G engineers wanted to use. They sit between 30 and 300 gigahertz. As the name suggests, the waves are tiny, from 10 millimeters down to 1 millimeter. For decades, radio engineers considered this part of the spectrum to be garbage frequencies for mobile communication. Why? Because millimeter waves are incredibly fragile. They are so small that they don't wrap around obstacles. They get blocked by almost anything. A tree, a wall, even your own hand blocking the antenna can kill the signal. Rain absorbs them. Oxygen absorbs them. Using millimeter waves for mobile phones sounded insane. It would be like trying to light up a whole room using a laser pointer while someone is constantly walking in front of you. If you put a standard antenna on a tower and tried to broadcast millimeter waves in every direction, the signal would die before it reached the end of the block. But the engineers realized that the weakness of millimeter waves was also their greatest strength. Because the waves are so small, the antennas needed to catch them can be tiny too. And if the antennas are tiny, you can pack a lot of them into a very small space. This is the first major aha moment of 5G. It is not about finding better waves. It is about changing the geometry of how we send them. It is about a concept called beamforming. Let's use an analogy. Imagine that crowded room again. The old way of doing things, broadcast radio, 4G, is like standing in the middle of the room and shouting your message. You are an omnidirectional radiator. Your voice goes everywhere. If you want to talk to someone 10 feet away, you have to shout loud enough for them to hear you, which means everyone else hears you too. You are polluting the entire acoustic environment. Now imagine if, instead of shouting, you could create a focused cone of sound that traveled directly from your mouth to the listener's ear and nowhere else. You could whisper, and they would hear you perfectly, but the person standing next to them would hear silence. If everyone could do this, thousands of people could talk in the same room without any interference. This is what beamforming does. But how do you make a radio wave, which naturally wants to spread out like a ripple in a pond, stay in a tight beam? You can't just put a blinder on it like a horse. You have to use the physics of interference. Imagine a calm pond. If you tap the water with one finger, a circular ripple expands outward. That is a standard antenna. Now imagine you have two fingers. You tap them on the water at the exact same time. You create two sets of ripples. Where those ripples overlap, interesting things happen. In some places, the crest of one wave meets the crest of the other. They add up, creating a double-sized wave. This is called constructive interference. In other places, the crest of one wave meets the trough of another. They cancel each other out, flattening the water. This is destructive interference. Now, imagine you have 100 fingers, a massive grid of them. This is what we call a phased array. By carefully controlling exactly when each finger taps the water, delaying some by a fraction of a microsecond, you can manipulate that pattern of interference. You can arrange it so that all the waves add up to create a massive spike of energy in one specific direction and cancel each other out everywhere else. You have created a beam, and because you are controlling it electronically, just by changing the timing of the taps, you can steer that beam instantly. You can sweep it across the room. You can lock it onto a moving target. This is the heart of 5G. A 5G tower is not a dumb pole blasting a signal. It is a smart array of dozens, sometimes hundreds, of tiny antennas. This technology is called massive MIMO, multiple input, multiple output. When you pull out your 5G phone, the tower detects you. It runs the math and fires a precise beam of data directly at your device. As you walk down the street, the tower adjusts the timing of the waves, steering the beam to follow you. It can even bounce the beam off a building to reach you if you are out of the line of sight. This is why 5G can handle so much more data. It is not just that the pipe is wider, it is that the tower can send different beams to different users on the same frequency at the same time, without them interfering with each other. It is spatial multiplexing. We are not just slicing up the frequency, we are slicing up the physical space of the air itself. However, the use of millimeter waves and beamforming is only half the story. There is another layer to this black box, an unseen giant that makes the system truly revolutionary. It solves a problem we rarely think about: latency. We often confuse bandwidth with speed. We think if we have a fast connection, it means we can download big files quickly. But that is throughput. Latency is different. Latency is the time it takes for a signal to make a round trip. It is the reaction time of the network. In 4G, the latency is usually around 50 to 100 milliseconds. That sounds fast. For a human watching a video, it is fine. But for a machine, 50 milliseconds is an eternity. If you are a self-driving car moving at highway speeds, in 50 milliseconds, you have traveled several feet. If you are a surgeon operating a robotic arm remotely, a 50 millisecond lag means your hand moves on the screen after you have moved it in real life. It feels disconnected. It creates motion sickness. It is dangerous. To get to the tactile internet, where actions feel instantaneous, we needed to get latency down to 1 millisecond. The physics of light says we can do it, but the architecture of the network was in the way. In previous generations of cellular networks, your data had to travel from your phone to the tower through a series of routers and switches deep into the core network, often hundreds of miles away, to be processed and then sent all the way back. It is like having to drive to the main post office in the city center just to hand a letter to your neighbor. 5G changes this topology through something called edge computing. Instead of sending all the data to a central cloud, 5G moves the processing power to the edge of the network, right there at the base of the cell tower or in a local aggregation point. It brings the brain of the internet closer to the user. But there is an even deeper principle at play here, something called network slicing. This is where the physical reality of radio waves meets the virtual reality of software. In the past, the network was monolithic. Everyone was on the same road. If a teenager was downloading a 4K movie, they were competing for the same resources as an ambulance trying to send patient data. It was a first-come, first-served system. Network slicing allows operators to carve up the physical infrastructure into multiple virtual networks. It is like looking at a highway and magically designating one lane that is only for emergency vehicles, one lane that is for heavy autonomous trucks, and one lane for general traffic. But these lanes are not fixed, they are dynamic. They can be created and dissolved in seconds. This relies on the virtualization of hardware. The specialized boxes of wires and circuits that used to run telecom networks are being replaced by software running on standard servers. This allows the network to adapt its shape. For a self-driving car, the network creates a slice that prioritizes ultra-low latency. It doesn't care about downloading a movie. It cares about getting a stop signal immediately. For a smart water meter in your basement, the network creates a slice that prioritizes battery life and connection reliability, even if the data speed is incredibly slow. For a stadium full of fans, it creates a slice for massive bandwidth to handle thousands of videos. These slices run on the same physical hardware, the same antennas, the same fiber, but they operate as completely separate networks. This is the profound shift. We are moving from a hardware-defined network to a software-defined network. The rigidity of the physical world is being replaced by the flexibility of code. So, let's step back and look at the whole picture. We started with a simple user experience, a phone that works instantly, everywhere. We peeled back the layers to find a spectrum that was choking on its own success. We saw how engineers stopped trying to fight the laws of physics and started using them to their advantage. They took the useless millimeter waves, the ones that couldn't travel more than a block, and used that limitation to build denser, more capacity-rich networks. They took the chaotic ripples of radio broadcasting and tamed them with the precision of phased array beamforming, turning floodlights into lasers. And they took the rigid, centralized architecture of the Internet and shattered it into a flexible, decentralized cloud that lives right next to us. There is a common misconception that 5G is just about faster download speeds. We think it is just about downloading a movie in 3 seconds instead of 3 minutes. If that is all it was, it would hardly be worth the billions of dollars in infrastructure. The reality is that 5G is not really designed for phones. It is designed for everything else. It is the connective tissue for a world where everything is a computer. It is for the sensors on a bridge measuring stress, the cameras on a traffic light monitoring flow, the drones inspecting power lines, and the autonomous trucks forming convoys on the interstate. When we understand the first principles of 5G, the constructive interference, the millimeter wave propagation, the network virtualization, we realize that we aren't just building a faster phone network. We are building a nervous system for the planet. We are creating a layer of responsiveness that allows the physical world to react and adapt at the speed of digital thought. We used to think of the air as empty space, a void between things. But through the lens of these technologies, The air is becoming a solid medium of information, as tangible and structural as concrete or steel. We are filling the silence with a symphony of invisible, directed, and intelligent beams, orchestrating the movement of the world around us. And that, in the end, is the true magic of the density of air.
You've been listening to First Principles. Until next time, stay curious.